Hi, everyone. So today I'm going to talk about chapter 18, global climate change. I'm a little bit, probably 1 week off the schedule. So we have one more chapter, then we'll have our midterm exam. So it's time to review material. I will try to post some review questions to the Blackboard and start to review them. Okay. Um, So hopefully will be helpful. The exam will be online, and I will post the link, and you can do that anytime you want within a week, and then submit that. Right. Okay, so without further ado, I'm going to start to do global climate change. The reason I bring this forward is because you will see that a lot of natural disaster after midterm we're going to learn mostly natural disasters. Lots of those is related to global climate change. So I thought that maybe we can learn this ahead of time so that you have a better understanding of the natural disasters, why they occur, and how we can adapt to it. Right. Okay, so before doing that, first, I'm going to clarify one concept, which one is, and now we talk about global climate change. So what's the difference between the climate and weather? Weather is you check your phone every day. There's a weather forecast. So that tells you the temperature, the humidity, the wind speed, and so forth. Whether it's precipitation, whether it's raining or not, sometimes has cloudiness, whether it's sunny sky or there's cloudy and so forth. So those are weather, and when we talk about global climate change, climate is still different from weather. So let's first watch a video, and I think that's a very good um, illustration of the difference between the weather. Hmm? Oops, what happened? Okay, so that was the I thought the very detailed explanation, distinct making draw the very distinct the distinctions between weather and climate. So again, we're gonna go to the case history, case study, and um, the case study is the potential consequence of global warming, and then there's a famous quote by George Santayana, and he said that those that cannot remember the past are condemned to repeat it. So this basically means that we need to learn from history. For example, in terms of global warming or climate, we have to know what happened in the past. All right. So the case study is if we look at Earth's history, the instrumental record, which shows the global temperature. So here is a famous plot, and there are instrumental record. We only have, you see that our thermometer was actually invented in 16th century, so 15th, 16th century. Only at that time, we start to have real measurements of the Earth's temperature. So, and then before then, we all need some kind of proxy data. So instrument record is the black one. So that's the one. It's in the 18th century. And that's when, after we have the thermometer is invented. And now before then, we have things like borehole data and some other proxy data, glacial length and so forth, and tree rain data. So they actually gave us some information about the Earth's temperature. This is a relative temperature. This is we call it temperature anomaly. This is relative to baseline. I think it was like 1950. That's the baseline. So you can see that it's zero is here. Now from this plot, you can notice that in the last 1,000 years, Earth actually experienced a warming and cooling period. So, for example, the famous about 300 years period, about 1,000 to 1,300, that period, you see that's some of the records, especially my proxy record, the trade wind is probably exceptional. But other records all show that at the time, the Earth's temperature is actually as warm as like Earth's 1950s. So there's a name for that. We call that medieval warming period. And then after that, there's actually has a cooling period in about 1,500 years. So the Earth's temperature is actually cooler than current one by about a degree. And there's a name for that. We call that little ice age. And then they come back. And recently, you see that it's getting warmer and it's warming fast. So you see that's kickoff. And this plot, especially this part, we call that it's like a hockey stick model, which means that it's like a hockey stick. So this is a long tail, pretty flat, and then it increases dramatically. Okay. So in the medieval time, about 1,000 to 1,300 years, there are, that kind of climate, there's, we'll see that there's winners and losers since the beginning of time. For example, that warming period, there's a flourish of cultural and activity because it's warmer, so you have more food, more harvest, and then you see that there's a flourish of cultural and activity and expansion of the population, and as people prosper. And during that period of time, many Europe grand cathedrals were actually constructed. And also during that period of time, the first global trade routes opened from Europe to China, connected by favorable climate and camel caravans. Also, at that period of time in North Atlantic, the sea temperature is warmer, and then there's less sea ice. So the famous Viking explorer Eric the Red's voyage near the end of the 10th century, that's because of the warm period of time, they were able to arrive at Greenland with their ship and people. They set up settlements that flourished for several hundred years, and they were able to grow into a variety of crops, into corn, and then and then they were able to raise animals in general, and then they have a pretty prosperous time. So today's temperature is about 4 degrees warmer than now. That's based on some kind of calibrations. And also during the same period of time, Polynesian people in the Pacific, they take advantage of those winds flowing through the Pacific, and they were able to sail to and colonize islands over vast areas of the Pacific, including Hawaii. So those are winners. And also during the medieval time, there are also losers and associated with warming period, like when there's warmer, like North America, Central America, in the West Coast, normally it responds with a drought and dry times. And in some cases, people just move it away. And like in the Sierra Nevada in California, the Native Americans, they can just move, they moved away, relocated to places that is has more water. And some people suggest that the Maya civilization in the Yucatan Mountain of South Mexico and Central America was actually got strongly affected in the process, and their society actually collapsed because of this drought. Okay, after that, there's a little ice age, and that's in the middle, 1400 to 1700, about 300 years. And for a little ice age, it's also that there are winners and losers during this cold cooling time, especially in Europe. And it's making people very difficult in South Asia, West Europe, and to live. So, and with climate change, the monsoon rains weakened, and the water became scarce, and the anchoring civilization was declined by the 15th century and collapsed by the end of the 16th century. And the collapse was gradual, and people left the city, moving to a smaller community. And why this kind of collapse happened, it's never fully understood. But some people think that it's something to do with this little ice age. The crop failure in the Western Europe during the little ice age, population devastated by the Black Plague, about 1400 years. And the storms, wet periods, extremes of heat and cold, climate change caused a number of problems. Some winters very cold, and during a very cold winter of about 700, this part of the time, the river Thames River in London was actually frozen solid for 2 months, which is pretty rare. And sea ice extended for kilometers in the North Sea, closing harbors and restricting shipping and crop feeders in Western Europe, and population was devastated by the Black Plagues and reaching out into the Atlantic and Iceland by about 1480. So this is it also they have famines, spread of Black Plagues, the climate change believed to cause the dormant of Viking settlements in North America and Greenland. So the cooling time, those are the losers, but some other places may have rain, like in the Central America, they actually become to be a little wet. They actually help them. So can see that even in the last 1,000 years, before we talk about global climate change, we saw that the global climate is always changing. And there's a warming time and there's cooling time. And these days, later, hopefully at the end of the class, I will help you convince you that most of these changes are due to the anthropogenic CO2 output. Okay, this is another figure showing from 0 to 2,000 years record. These are different record, instrumental record, approximate record, and the borehole record, framing record, and so forth. And the one that we know for sure is these guys, the hockey stick model, and it's project that we're going to go to very, very high. And from the last 2,000 years, the Earth's temperature roughly changed by about from this hockey stick model to about 1,700 years. Also, the Earth's temperature changed about 1 degree-ish. And if we think the whole spectrum That's about 1 degree-ish. But people project that in the future we're going to have much higher temperature. All right. So global change overview. So the climate change basically contributed to the complex evolution of Earth's history. We just used the example of the last 2,000 years. And in order for the Earth system, so this climate change is involved in the Earth system, and basically which is the focus of the interaction among the atmosphere, oceans, solid Earth, and the biosphere. And these we call the as reservoirs or systems. And there's a class I'm teaching, which is Earth system science. Basically, we talk about the interaction among these different spheres. And the climate, the vital zone, the life zone is actually the place where all these systems interact with each other, the interface. All right, so the global climate, the global change, the environment change has the effect of human activities and the global levels. One of the famous Earth scientists, his name is Preston Cloud, is there. He studied the history of life on Earth and also the human impact on the environment. And he proposed that there's 2 central goals for Earth sciences or Earth system sciences to study. First is understand how Earth works and how it was evolved from the landscape of barren rocks to a complex landscape dominated by the life we see today, and then apply these understanding to better manage our environment. So this is basically central for our environmental geology. We have to first learn how Earth works. Then we apply this information to better manage our environment. Okay. So what are tools we study global change? First, we have to know what happened in the past. Okay, so we need some kind of geological record. The first kind of geological record are the sediments. The sediment deposit on, for example, floodplains or in lakes, bogs, glaciers, or in ocean. And they can be compared as a history book. And each layer, you see this different color, okay? And the forming layers. And after some time, they deposit one layer. It takes some time. Sometimes take about millions of years to deposit a thick column. And then there are inside there's organic matter with sediments. You can date them. You can sediment, and then you can also use other ways to date the sediment rocks, and which give you a chronology, give you a time dimension. And then the organic matter can tell you a story concerning the past climate, life forms in the seas. For example, if there's lots of organic matter, you know that there's lots of activities. There's favorable conditions for life, example for plants, and then we can use those to infer the past climate. And also, there are also shells of organisms, and the shells, especially carbonate or silica, they can actually record the seawater information, and then give us an estimate of what happened in the past. So the second kind, the sediments, this is quite important. The second kind is this the glacial, the ice, sea ice, not the sea ice, the ice. So this is ice core. Basically, you drill a core from the, for example, Antarctica, then you can look at the bubbles trapped in those ice. So normally what happened when later explain that when you have snow, then the snow will compact. In the snow, there's a lot of air bubbles, and then it's gonna compact. So basically under gravity, they're gonna compact. And then basically what happened, the air, most of the air is being squeezed out. And then, but you still have little air bubbles trapped, frozen inside of those ice. And then we study the concentration of like CO2, carbon dioxide, and then methane, for example. Then we can correlate with some other record, proxy record, like what I said, the diatoms or forams, their skeletons, they have isotopic composition. They actually can are sensitive to temperature, for example, and then you can correlate with that. You can see that this is, you can look at this ice core record, you see that atmosphere CO2 concentration is changing varying between 200 to 250 ppm in the last 800,000 years. Only recently, it doubled. It pretty much doubled. And then this is correlated with also the methane concentration and also with the temperature record of the ocean. So these give us an estimate, understanding of what happened, what caused the temperature change or climate change in the past. Sometimes we also use real-time monitoring. So for example, this is a famous plot, and this is actually in 1960s. People use the spectroscopy data, like the famous in Mauna Kea, they use this infrared spectrum and to measure the concentration of CO2 in the atmosphere. And this is the record. And the in general trend is increasing from 1960s, it's about 300 ppm to 2010, that's about 385 ppm. And then you see that the record is not smooth record, it's actually zigzag. This is because there's annual cycles of CO2 concentrations in the summer, where you have in the northern hemisphere summer, you have more plants, and they do photosynthesis, therefore they draw down the carbon dioxide concentration, they drop by a few ppm. Whereas in the winter, where plants, especially plants doing photosynthesis, they die, or they're not working. Therefore, more CO2 from animals to be generated, and therefore concentration of CO2 in the atmosphere will be high. So you see this annual changes, but the change of annual change is about like 10 ppm-ish, very small quantity there. But this is an instrument record that's very good for testing models and predictions from the historical record. And also for scientists, we use some kind of models. And this is the one, this is an idealized diagram illustrating the cells. So basically what we're going to do is this is just, this is the globe and our Earth. And then we divide it into different grids. In each grid, there could be ocean, land, the air, and also we call that each cell. So we divide into Earth to atmosphere into different cells, and there in the cell there are cloud, continents, there's ocean water. Then we calculate what are the interactions, what are the heat budget or the solar energy coming to the Earth's surface. Then some will be reflected, some will be absorbed, and then the heating of the Earth's surface. And then we can actually predict what happened what's the Earth's climate or temperature is. And then we can compare with the past record. And then after that, we can be used to predict what happened in the future. So we call that a global circulation model. Basically, it's a mathematical model, but it can include all the topographies, continent, ocean, and also atmosphere. We look at the interaction among them using very sophisticated algorithm to calculate Earth's temperature variations, and we compare with the instrumental record. So for example, this is this observed record, instrumental record. This is calculated, and you see that within about 0.2 degrees, they're actually pretty close to each other. And this is different kind of simulations. Okay. And then you actually can see there are a few volcanic eruptions, and Pinatubo, for example. And then you see that it's predict that there's a drop in temperature by about 0.5 degrees, and the Alchicon volcanic eruptions, Agon and Santa Maria volcanic eruptions, each time happened, and it can cause the global cooling later on top of volcanic forcing. Then I'm gonna come back to this. Okay, so these are the tools we use. We have geological records, sedimental records. We also have things like tree rings. We study carbon dioxide concentration in glacial ice from ice core data. We have real-time monitoring that can be used to test models. Then we have GCM models, global circulation models. So before we talk about climate, first let's look at Earth's atmosphere. So basically, climate is a reflection of the Earth's general atmosphere conditions. And so here is a structure of Earth's atmosphere. So you can see that Earth's atmosphere divided into 4 or 5 layers. There's another layer which is called ionosphere. But most important things are the 4 layers. One is called troposphere. It's about 10 to 12 kilometers. And inside, and so here, the curve here is the temperature. So basically, how we define those different spheres, we look at the temperature variations. So on the surface, most of the heat is actually absorbed by the Earth's surface. Therefore, the surface is warm. Whereas the atmosphere is actually not a heat absorber, good heat absorber. So as we go higher latitude, altitude, the temperature is cooler, and then it reach the maximum. The maximum we call that a minimum. We call that tropopause, reach the minimum, which is about 42 degrees Celsius. And then after that, the temperature actually increases. This is because in the stratosphere we have ozones. The ozone absorbing UV light and then heat up. So therefore, the closer to the sun, the more ozone, more UV light absorbed, the atmosphere will be heated more. So temperature increases, and then to about 0 degree-ish, about -5 degree-ish. So this we call it stratosphere. Why it's called stratosphere is because the bottom of the air have low temperature, therefore they have high density, whereas the top of the stratosphere are warmer, therefore has low density. So the air is very comfortable sitting in this kind of conditions because the bottom is heavy, top is lighter, therefore the air is actually stratified, which means that they actually will not going down. Whereas troposphere is opposite because on the surface, in the low altitude, the air is warmer, therefore they have lower density, then they will rise. And when they reach to the tropopause, the temperature decreases, and then the air becomes too dense, then they're gonna settle down. So then you have this kind of convections. So in the troposphere, there are lots of convections, air is turbulent. So therefore, most of the aircraft, they want to flow in the stratosphere or affected by the jet stream and so forth. They want to do this. So in the troposphere, we have lots of weather phenomena like storms, hurricanes. They all happen in the troposphere, whereas stratosphere air is stratified. Then you're going to the mesosphere, about 50 kilometers high, and then the temperature decreases again because you don't have a lot of ozone. Therefore, this part have ozone that absorb heat, and it's getting warmer. The density of the air getting lower. Therefore, the temperature cools down as you go into space. And then when you're going to make a turn at about 80 kilometers, where the air molecules, upon the temperature, upon the shining of the sunlight, then the air molecules sometimes can be ionized, then it becomes to be a thermosphere getting warmer and warmer as you're going towards the sun. So here is the atmosphere pattern, and what we care most is the troposphere. Most of weather phenomena is the troposphere. For the climate, sometimes we consider the stratosphere. We say the stratosphere have some kind of contribution to the troposphere, sometimes heating and warming, because the heat eventually has to go through, when we reflect back to the space, it will go through the stratosphere. All right. So because Earth is rotating, if we only look at the troposphere, and because Earth is Earth's rotation, and then normally in the tropical area in the equator, the air being warmed up by the sun, and they will rise. So there's a low pressure zone. Whereas because Earth's rotation, it cannot go all the way to the North Pole or South Pole. It's actually in the middle of that. It's about 30 degrees. It's actually already changing directions because of Coriolis force. So the air moving to this direction on the upper part of the troposphere, and then they will turn in the northern hemisphere. They turn to the right. So basically, by the time it go into here, the air is actually parallel to the latitudinal line. It's actually not going north and south anymore. And then as a result, in the 30-degree, have a high pressure zone in the ground, the air moving from the high pressure to zone low pressure, then they're going to turn right. So then we have this kind of trade winds developed. And then this is actually is something called that the Halley cell. It's a cell. And then going to the high latitude between 30 to 60. Then we have another cell, it's called ferrous cell. And then from polar region, we have polar cell. And then air moving to different directions due to this wind patterns. So this is latitudinal distribution of the wind. And the weather and climate actually are affected by this movement. This is caused by the uneven distribution of heat. Therefore, when there's hot, the air will rise, whereas cold, then air will settle down. Therefore, we generate the high pressure zone, low pressure zone, and have three cells. Okay, so this is a general latitudinal distribution of the wind. And then because that Earth actually can be divided in different kind of climatic zone, that's controlled by this global circulation movement of air mass. So we can divide into different climatic zones. For example, this is example. So here in different places, for example, the different places have a characteristic temperatures and precipitation conditions. And so, for example, this is humid subtropical area in for example, China. So this is the annual temperature change, and that's the precipitation. And in June, July, August, and summer have more precipitation. Whereas in this place, there's a monsoon. In India conditions, then you have the temperature at almost constant. Does not change too much, but the precipitation is changing a lot. And then you have places like Arctic conditions. Temperature is very dry, precipitation is very, very low, and the place equatorial, it's pretty wet. Temperature in the equator, temperature does not change too much, but precipitation changed a lot. So based on these different kind of effect by this global circulation, and then the Earth actually been divided into different kind of climate zones like Arctic zones, ice cap, continental, subarctic. Humid, continental, tropical, wet, dry, and also mountains, monsoons, equatorial, wet, and desert, and so forth, Mediterranean. So these are all different kinds of zones. Each one has its characteristic temperature variations and also precipitation variations. So here is atmosphere is very complex chemical factory. And with many little understood chemical reactions. Many of the reactions strongly influence both the sunlight and compound produced by life. So here is example. For example, the atmosphere contains nitrogen, oxygen, argon, water, CO2, methane, and nitrogen oxide, and ozone, so forth, and also aerosols. And then we have different hydrological processes like making cloud, precipitation, and these. Some aerosols can be rained down. And we have volcanic activities that supply carbon dioxide and water. And then we have glacials and the hydrological cycles, the streams bring some of the material back to the ocean. And then we have evaporation and so forth. And this is, you can see this is a whole system, including all different kind of reservoir atmosphere, hydrosphere, biosphere, geosphere, they interact. At the life zone, and then all these processes contribute to change in the concentration, like greenhouse gas, and contribute to the different kind of temperature. For example, if you're close into the ocean, at the beginning warmer, whereas if you're in England, in the continent, at high altitude, then it's cooler. So these are all play some roles in changing temperatures. So before talking about climate change, I want to emphasize something we call greenhouse effect. Greenhouse effect basically is due to the energy budget. Thinking about Earth's energy budget, it's controlled by a few things, like the amount of sunlight received. These days, currently, we have about 1.37 kilowatts per square meter. That's about solar energy input to Earth's surface on average. This is on average, okay? This is, as we know, that tropical area has more and the equator have more, and whereas polar region has less than this number. And this is just average. And also the amount of solar energy reflect, some solar energy being reflected back to space and some being absorbed. And the one that affect the climate is those absorbed. The amount of energy, heat, and tension by atmosphere and also by ocean, they are very important. So that's determined by the three factors. Now, the solar energy, remember that they actually have a full spectrum from very short wavelength and like gamma rays, X-rays, to very long wavelength, even radio waves. They have a full spectrum of electromagnetic radiations coming to Earth's surface, and the visible light is only in this small region. Okay, so actually the full spectrum of energy coming to us. Whereas what the long wave ones have very small quantity, a small amount of energy relative to the high energy ones. Now, Earth's atmosphere is very good at of absorbing low wavelength energy, especially the infrared region somewhere here. Whereas this high wavelengths, the high frequency or low wavelengths electromagnetic radiations, light, will actually going through the atmosphere without any problem, whereas these long ones has troubles. So here is a cartoonish plot to illustrate how this kind of balance happens. So this is 100% incoming solar radiation, and it's about 30% of reflect space, 25 from atmosphere, mostly things like cloud. It's very important to reflect the solar radiation. Then the surface, only 5% are being reflected to the space by surface. Those are high energy, high frequency spectrum, so they reflect by space, whereas about 25% absorbed by atmosphere, 45% absorbed by Earth's surface. So 30% reflect by space. So if we talk about Earth's albedo, reflectivity, which is about 30%, 70% absorbed, and 45% absorbed by space, by surface. Now, when these energy absorbed by surface, once they absorb, they will turn into heat. And the heat, the Earth's temperature is about 300 degrees on average. So 300 degree Kelvin, talking about ish, so therefore these radiation going back to space actually turn into infrared region. So if you learned the physics like black body radiation, then the lower the temperature, the lower frequency, the energy will be radiated out from that black body radiator. So when these energy turn into short, long wavelengths infrared light, they can be absorbed by the Earth's atmosphere, and later, especially things like carbon dioxide, water, methane, and so forth, and eventually they can be trapped in the atmosphere and keep the Earth warm. So this is another cartoon saying this is this is where I mentioned that this is solar radiation, and you see that the sun is actually full spectrum right now. It's by 1 micron. That's a peak in visible light spectrum. That's visible light, and then this tail down at the infrared region, and then this is Earth's radiation, because Earth is cool, so the Earth is actually mostly radiating infrared region. Whereas these greenhouse gas like water vapor and carbon dioxide, methane, nitrogen oxide, and CFCs, the chlorine, the chlorine, fluorine, carbon material, they can trap more heat, and then they can warm up the lower atmosphere, and similar to the effect of the greenhouse gas. It's similar to the effect of greenhouse, putting the greenhouse. So the Earth's surface is about 5,526 degrees, and the Earth is only 15 degrees on average, which is 288 Fahrenheit, so on average. So therefore, they emit all infrared spectrum, and therefore one when the heat coming inside into the Earth is actually not, only 25% will be absorbed. And once it's turned to heat, and then they will be actually trapped by greenhouse gas. So therefore, the higher the greenhouse gas, then there will be more heat trapped in the atmosphere. Therefore, the Earth's surface will be warmer. Okay, so normally people said that these days we know that the major contribution of greenhouse gas is the human activity or anthropogenic gases. So here is another view. So basically, energy input is a solar energy that warms the Earth's surface. They're going through the Earth's surface without any problem. And once it's turned to heat, then they will be trapped by Earth's atmosphere and get trapped here. Okay, and then so this is basically the greenhouse effect. Now, I want to emphasize one thing is even though we said this global warming, the greenhouse gas is causing global warming. Okay, now the question is, the biggest greenhouse gas is actually water vapor, and the Earth actually, this greenhouse gas is very, very, very important for Earth. Without greenhouse gas, Earth will be warmer. Will be like minus 17 degrees Celsius. Okay, so the greenhouse gas is actually a natural phenomena, and that occurs for millions, billions of years. So here's history in the Earth originally in Earth long time ago, and then the Earth was actually even warmer than now. And then we have even more carbon dioxide in the atmosphere. And some people said that when Earth was first formed and Earth's atmosphere is full of carbon dioxide, it's like 50 atmosphere pressure of carbon dioxide mostly. And gradually with time, as the Earth evolved and also the evolution of the biosphere, then the carbon dioxide concentration decreases. So if without the heat trapped by the greenhouse gas, then Earth's actually very, very cold, which is actually not habitable. It's not going to be habitable. It's actually habitable. Now, the one we care about these days, why we care about these greenhouse gas, why anthropogenic greenhouse gas, is because we produce a lot of them. So here is diagram. Showing the, some of them coming from the instrument record, and we only have like 80 years of record, roughly 60, 70 years of record, instrument record of CO2 in the atmosphere. Then after that, we're all coming from the ice core data, and then you can go to like 800,000 years of history. And we just show that the carbon dioxide concentration in the atmosphere and methane and nitric oxide, these are the major greenhouse gas. And you can see that before industrialization, and they are pretty flat. Okay, it does not have significant changes. It's only happened after the industrialization, especially carbon dioxide, methane, they all kick off at that period of time. And then after that, then they cause the global warming. So this is something we these days care about most. You can see that natural cycles, without industrialization, we are kept pretty flat. CO2, methane, nitric oxide. The greenhouse gas concentration always kept constant. And they have a sudden increase or steep increase is due to human activity, especially after industrialization, we burning fossil fuels. Okay. So the instrument record from 18th century and coming from about 7,000 stations, it gave us the temperature record of the past, and then we showed this before. Yeah, we showed this. So these instrument records based on 7,000 stations they record. Of course, some of them have not complete record, and we rely on these. So then we talk about other sediment record and Also, we have historical record, for example, the books, the newspapers, journals, and articles. We have that. And we have a proxy record. So as mentioned before, the thermometer was invented in the 17th, 18th century, whereas the record we have is far before that. And most of them based on some kind of paleo proxy record. So proxy data refers to data not strictly climatic, but that can be correlate with climate, such as temperature of land and sea, ice core, tree rings, pollens, corals, and carbon dioxide, methane data. We actually can correlate with temperatures. So here, example of the tree rings. So this is the tree ring. There's dead trees, and there's living trees. When the trees die, then they have these to generate the rings, because tree when they grow, they actually. So the center will be older. That's the first small. When they're small, they grow. Then they grow wider and wider. So the tree barks and going to further and further away. Then every year they make one ring. So from this, it's easy to date them. Okay, and then you make a tree core, and then you can do some kind of correlation based on their the distance between those different rings. And sometimes when it's cold, then the tree does not grow too much, so the rings are very tight, very dense. Sometimes it's very warm period, then you see the tree rings are actually wider, and because it has more tree had growth. So this actually tells us some kind of climatic information here. So you can compare the old trees with young trees, and then you can do this kind of correlations, and then you can come up with the dates, easy to date them, especially from living trees. You can date them, and then compare with the old trees, and you can generate a year record. This is correlations like a barcode. Some part is close together, some parts wider. Then you can generate some kind of barcode, establish a chronology, and then from the dense and undense, you can actually tell the climate. And these dates also can use carbon-14 to date these tree rings and give a precise date about each ring when they grow. And from that, you can give some climatic information as well. And last time we mentioned that there's core, there's ice core data. They show that the instrument, the carbon dioxide variations in the last 800,000 years pretty much have some kind of periodic changes in their carbon dioxide concentration or methane concentrations. However, in the last few hundred years, after industrialization, then CO2 actually goes up very quickly. So global warming, we see that there's observed increase in Earth's average temperature of the near surface and ocean and land, and also warm Earth. And in the last 100 years, most of this process is caused by human burning fossil fuels. Also, there are natural ones. These are the natural processes. Also, there's natural response to humans' anthropogenic CO2 global warming. And because this record, we can see that the recent global warming can be attributed to the emission of greenhouse gas, and also based on the equivalent amount of global warming potential, carbon dioxide account for about 85% of the global warming because they have higher concentration. And you see that methane is ppb, parts per billion, whereas CO2 is part ppm, and nitric oxide is ppb. So the carbon dioxide concentration is far more than methane and nitrogen oxide, but even though they actually have bigger effect than carbon dioxide. And the water is actually also has greenhouse effect, but we normally don't consider them because we always have ocean. Also, there's a contribution from chlorofluorocarbons, CFCs, that actually contribute some amount, 2.2%. So this is 100 years of in the last 100 years, it's basically growing volume of evidence showing that the anthropogenic CO2 is the main cause for global warming. Okay, so let's look back a little further, rather than looking at 100 years of history, we look at even longer period of time. So in the Earth's past, the global temperature change in temperature over different period during the past many years. So let's just look at the Pleistocene, which is about the Ice Age. It's about 2 million years, and that's peaked about 18,000 years ago. So basically 18,000 years is here. So, and then this is Holocene maximum, and this is about 18,000 years here. That's the peak. That's the coldest time in the last glacial maximum. That's the maximum, and this warms up gradually, 18,000 years ago, and this warms up, and then they go into actually a younger dryas, and this is because there's several hypotheses about why they have inner dryas. Why this kind of warming is not as smooth. So it's during younger dryas, it's getting cold, and they go into Holocene maximum, then go into the medieval warming period, the Ice Age. So this is basically the history. So in general speaking, there is actually we are in the interglacial cycles. So if you look at the last 100,000 year cycles, then Earth is actually getting cold, warm, cold, warm, cold, warm, cold, warm. And then there's sometimes actually even warmer than us. So there's many cycles of warming and cooling period. That's a lot of time people contribute that into this changing carbon dioxide concentrations. Okay, so we have warm and cold period. And then the last 18,000 years after the peak of the last glacial maximum, then it's cold, then getting warmer and warmer, and then this colder and warmer, and we reach a Holocene maximum. It's about 6,000 years ago. Then it's getting cooler, and then a little Ice Age. Now we're actually going up again. All right. So you can see that the temperature change, the first order. In the first order, we have glacial interglacial cycles. Then in each glacial interglacial cycles, the warming is not smooth. It's not going to be going straight lines. Sometimes it warms cold, it warms cold, but in general trend, it's actually getting warmer. Okay, now this part, present day, we're in the glacial cycles. So based on this pattern, we have Holocene maximum. So actually in 1970s, the scientists from American Academy of Science, they actually proposed that we're going to glacial period. So watch out, we're going to get cooler. And later in the 1980s, people find out that the greenhouse gas actually get us even warmer. So this is basically, if we looking at the natural cycles, if we believe this is the natural cycles, and we're expecting that we are actually after Holocene maximum, which is about 5,000 years ago, is actually started getting cooler and going into a glacial period. But instead, because of anthropogenic CO2, and we're actually getting even warmer. So we basically interrupt this kind of variations. A warming trend over the last 140 years, first 8 years of the 21st century, have the warmest temperature these days every year. There's a report saying that this year in 2024 or 2023 are the warmest time. So of the record. So there, which means that we're actually getting warmer and warmer. In the last 100 years, mean temperature increased about 0.8 degree or 1.36 Fahrenheit, which seems to be nothing. But if you're looking at this is average mean temperature. We're talking about the global temperature change by 0.8 degree. That's a big deal. Okay, that's a big deal. All right. So there are many evidence showing supporting the early 21st century rise in global temperature. Like, for example, warming since mid-1970s has been about 3 times rapid as previous centuries. The decade from 2000 to 2009 was the warmest decade. And actually 2010 to 2020 is actually these days is the warmest decades in the last 1,000 years. And there's warmest year on record. Every year we're actually breaking this record. There's since 1965 the average temperature Earth's surface has increased about 0.2 degree per decade. So this is general trend. We're really seeing that Earth's average temperature is warming. So I'm going to show you animation, and this is based on history record from 1880s and how the Earth's general temperature is changing. And you can see that even though the global temperature increases, but some places getting warmer, sometimes some places affect more, sometimes some places affect less. You can take a look at. So starting 1950s, you can see that the color changed to yellow and to red. And after 1980s, it's getting more and more red. Okay, now we are actually getting more and more red. So this is 2019. So you can see the northern hemisphere actually warms more than southern hemisphere. And this is very easy to see. However, you can see that this part is actually cooler. Okay, this is something to do with the ocean circulation. So say in the beginning of the century, this part actually warmer, actually Greenland. And as we go to 2000, it's actually getting cooler. And the reason is some people think that's because ocean circulation, also because Greenland is melting, the ice melting, then they form a cooler region. So very clearly, in the last 100 years, the Earth is getting warmer, especially northern hemisphere warms more than southern hemisphere. This is because the northern hemisphere has more land. Southern hemisphere has more ocean water, and water has high heat capacity. It can store more heat, therefore, it's not affect more than the northern hemisphere. Okay, so next question is why climate change? Why there's a climate change? So I'm going to talk about different things. First, I'm going to talk about the natural cycles. Why climate change natural cycles? The second thing, we're going to talk about different kind of forcings there. Okay, so first of order, the Earth's climate is actually controlled, if without humans' interference, is controlled by astronomical behavior. Something we call the Milankovitch cycle. So Milankovitch is the astronomer. So he studies the orbits of Earth revolving around the sun. And if you look at the historical record, for example, here, you see that glacial interglacial cycles almost normally has about a periodicity about 100,000 years. Very close. It's about 100,000 years. It's about 100,000 years, 100,000 years, 100,000 years, 100,000 years. So first order, there's about 100,000 years cycles. And after that, and then you can see some finer scales, which is about 40,000 year cycles and 20 to 50 year cycles. So why there's the cycles? Milankovitch believes that this is the Earth's climate will have a lot to do with how much solar energy coming to Earth, or the solar energy distributed on the Earth's surface. And so he looked at the orbit of the Earth and find out that the Earth's orbit around the sun is actually not a circle; it's actually an oval. And the sun is changing between the two focuses of the Earth, of the oval. So it can coming from this focus to the other focus. Earth is moving, so sun is moving between those two focus of the oval-shaped orbit, going back and forth, and that orbit, that periodicity is about 100,000 years. So one is coming here, so Earth on this circle, then when the Earth is coming to this side, it's closer to the sun, have more solar energy, whereas going to this side will be cooler, and so cooling at different times. So Earth will changing between those two extremes. So when Earth is getting warmer, closer to the sun, it will be warmer, and further away from the sun, it will be cooler. Okay, and so he believes that this is, and it has a periodicity about 100,000 years, and the Earth's orbit gradually changing from circular to elliptical, and then the sun, and then they're coming back. They have this kind of periodicities. So this is called we call that eccentricity. Eccentricity basically describe or the Earth's orbit revolving the sun is not a circular, it's actually oval shape, and the sun is changing between those two focuses. So it's called eccentricity. The second thing is we call that precession. Precession describes that Earth's the North Pole, okay, is actually not a fixed. We're thinking about the Earth's North Pole towards always going to the geometric pole, the rotation axis always towards the Polaris or North Star, but actually it's not. It's actually wobbles. Like you play with the drill, you do this, and you can see that even though the drill rotates, it can actually change its rotating axis a little bit. It's still be stable. So Earth turned out to have this kind of called precessions. This north axis actually wobbling around that central axis, and as with frequencies about 25,000 years. Okay, so we call that precessions. So Earth is like wobbling like that. This actually changes how the Earth seasons is. So for Earth, now we know that as we are in the December, the south hemisphere actually closer to the sun, okay, or pointing to the sun. The sun is pointing to the shine the light directly on the southern hemisphere, and because Earth's north axis is towards the Polaris. What if this actually going the opposite side? Okay, then the northern hemisphere becomes to be towards the sun in the winter. Then the winter will be summer. So because the precession and because Earth's axis, rotating axis, actually wobbles, and the seasonal variations are actually changing. For example, March 20th, that's the starting of June 21st, that's the starting today, that's the start of the summer. About 5,000 years ago, start of summer is actually starting at September 22nd. About 11,000 years later, before, the summer actually started at December 21st. And 25 years ago from now, March 20 is the start of the summer. So this is because this is wobbles. So we have this kind, we call them Minkowski cycles. So this is it's an effect. Now there's a third effect. There's also tilts, and there's 23.5 degrees. We know that from this degree, and then that also can change. The tilt can change a little bit. So these two things, wobbling effect and change, this rotation, the tilting, then they change not only 23.5 degree before these days, and this actually changes. Sometimes maximum is 24 degree, and some minimum is 21.5 degrees. So it's not perfect 23.5 degree. These days it's 23.5 degree. And this is the reason we have seasons. So the seasonality also going to change if we have different tilting. So different part of the northern hemisphere will be affected differently. So then the distribution of the solar energy will be different on Earth's surface. So therefore, and you can see, but this wobbling and this tilt axis changings are actually slightly actually related to these two. Therefore, these two combined together, the precession and also this tilt changes, and they gave us about 20 to 40,000 years of periodicity. So Minkowski first identified these, these changes, and hypothesized that this can cause a big change in Earth's climate in different places. So the long circle is variability in Earth's orbit around the sun, which is the oblique, because eccentricity, and whereas the short cycles is wobbly effect Earth's axis, and also the tilt angle, tilting angle of the axis, and then that's caused this 20,000 to 40,000 years of variations. So if we combine those together, so if we look at this precession, eccentricity, that's the periodic changes in the last 100,000 years, and then that has around 100,000 years of cycles. Then obliquity is the tilting angle changing from 23.5 to 21 to 23 degrees, then that's going to have a forcing like this. And precession, that's 25,000 years of cycles, that will be having forcing like that. If we combine those together, that's a total solar forcing, 65-degree summer. And then we'll have these all together, that's actually matches. This is combine these three things together, then we have this thing. This is the combined solar forcing that actually matches the stage of glaciation before the human invention. So to the first order, the climate change is due to the Milankovitch cycles, or astronomical positions of Earth sits in the solar system, or the interaction between the sun and Earth. That's actually contribute the natural cycles. That's actually coincide with the stage of glaciations. Okay, so these are, we call that solar forcings. And also beyond that, we have to consider the volcanic forcing and anthropogenic gas. And the currently, we have likely to have 1.5 to 4.5 degree of warmer in the 21st century, depending on what kind of strategy we use to curb the CO2 concentration in the atmosphere. So first, let's first look at climate forcing. Climate forcing basically consider all the forcing parameters, like including solar forcing, greenhouse gas forcing, and so forth. This is a simple way how we calculate how much temperature change, a global mean temperature change of the Earth. Normally, we use something kind of watts per square meters. That's could be positive or negative. When it's positive, that means it will make Earth warmer. If negative, it will be making Earth cooler. So these are basically all the climatic forcing parameters. And then there's also a term we call the climate sensitivity, and the response to how these climate forcing after a new equilibrium has been established, how much temperature they affect the Earth. And it also requires forcing to occur is the time response time, how long for this to respond. For this kind of forcing, they actually have different response time. The rule of thumb right now is that every watts per square meters of forcing can change the Earth's temperature by 0.75 degrees. So for example, if I have a total forcing of minus 6.6 plus minus 1.5 watts per square meter, 6.6, that can contribute about 5 degrees of cooling of the Earth. So this is a model for the last major ice age, the glacial maximum of about 22,000 years. So ice sheet and vegetation contribute minus 3.5 watts per square meter of forcing. That's about 4.5 degrees. And then you have greenhouse gas is very low, CO2, methane, nitrogen dioxide compared to now. That's actually much lower than now. Therefore, they have minus 2.6 watts per square meter forcing. Then aerosol is also low because it's cold. The total forcing, you add them together, is minus 6.6. And every watts per square meters is 0.75 degree. Then you can calculate that's equivalent to about minus 5 degree of decrease of global average temperature. Here is another example, which is the last 100 years forcing, like CO2 forcing, the CFCs, the greenhouse forcing, other ozone, black carbon, so forth. Then there's the reflective clouds forcing and solar forcing. As they act together, that's the total amount, and then you can calculate which is the total amount, about 1.6 watts per square meter. That corresponded to about 2 degree increase in the average temperature. So these are the climate forcing directly. Another thing can be affecting Earth's climate is the global scale circulation of ocean waters. So the climate system unstable in short cycles, in short decades. The ocean water, especially here, current forming, especially like the Gulf streams are very hot. They're moving to the Atlantic Ocean, and then they sink. And then they go into the Antarctic cold water, and then they go into Pacific, then they go into surface, become the warm shallow water, then go this kind of ocean circulation pattern. And this circulation is long-term processes. Okay, it takes about 100 to 1,000 years, but the amount of heat flow involved in this is actually equal to amount, people said, 100 Amazon rivers. So the amount of warm water and heat released to the atmosphere can also change the climate. So this is ocean forcing. Okay, normally these kind of things not considering ocean forcing, and ocean water is a high good heat capacitor. You know, they can store a lot of heat in the ocean water. So this can be very effective to change the climate. So every time after you consider these kind of climate forcing, you have to consider the ocean circulation, which redistribute the heat to every places. Okay, the solar forcing, I mentioned before that there's historical variabilities of the solar energy, and beyond the Milankovitch cycle, the solar also change its luminosity, periodicity, and there's 11 years of cycles. And also people see that the medieval warm period, about 1,000 to 1,300 years, that corresponding time of increased solar radiation, whereas the ice age, that's corresponding minimum solar activity. You can actually correlate with this with the sunspots activities, and then this is what people claim. And but this effect is relatively small, 0.25%, whereas the long-term change is actually due to culture cycles. So this is the last 100 years increase of the CO2 greenhouse gas. This example I mentioned before, that's actually caused this is solar forcing. Another factor is volcanic forcing. A lot of time we have considered volcanic forcing eruptions. They actually eject a vast amount of aerosol particles into the air, and those particles they reflect the sunlight and then reducing solar radiation. The episodic volcanic eruptions have a significant contribution to the cooling of a little ice age. That's what people said. And give example. So here is the several volcanic eruptions, like the Pinatubo volcanic eruptions cause the solar radiation change by a few percent, very small percent. And El Achicon, it changed by 3%. And people said that this Pinatubo, that's actually changing the Earth's average temperature by a degree, 0.5 degree-ish on that year. Okay, so volcanic forcing actually caused the global cooling. And all those dust actually does not last very long. If they're in the troposphere, they will settle down very fast. If you go into stratosphere, then they will have longer effect. Whereas lots of this SO2, that's actually when they go into the stratosphere, that can cause a cooling effect, a long-term cooling effect. Okay. As for anthropogenic forcing is also very, very important. That's basically talking about greenhouse gas. The mathematical modeling on the anthropogenic forcing, basically we talk about this, and that's contribute, total is about 1.6 watts per square meters. That's corresponding to about 2-degree increase in the temperature, and suggesting that this global warming is a result of human activities. Although the air pollution that can reduce incoming solar radiation by 10%, like the black soot, they actually can block some sunlight, cause a little cooling there. So the black carbon is products in complete combustion. It's visible in the exhaust of diesel fueled trucks, also produced by biofuels and outdoor biomass burning, and that they are not well measured, but their climate forcing is estimated from measurement of total aerosol absorption. The forcing includes the effect of soot in reducing and reflecting of snow and ice. So this is actually hard to very hard to determine, because some of the soot can absorbing the solar radiation, some of it actually reflect them, and then when the soot settle down on ice and snow, they actually reduce the albedo, reduce the reflection of sunlight by ice and snow. So it's actually pretty complex for this black carbon. All right. So the potential effect of global climate, depending on how we treat with greenhouse gas. So human activity increasing the concentration of greenhouse gas in the atmosphere. If we do business as usual, we see that the global temperature CO2 concentration will increase by significantly. Okay, so to thousands of ppm. And when it happened, then the global temperature average increase by 4.5 degree-ish. Okay, that's the maximum. If we do something, we actually can change that to 2.6 degree. Another thing is that, so this is the global warming relative to 1985 to 1900. That's the relative, that's 0, 960 is here. That's from 1.5 degree, depending on different kind of scenario, whether we have reduction in the carbon dioxide or not, or business as usual, and we will have different pathways. And please take note that even we completely reduce CO2 emissions, okay, it's like this, we completely emit this CO2, and you can see that the temperature of the Earth is not going to go down like a stone block. It actually maintains. So they have some kind of inertial there. Even though we completely cut off all the CO2 emissions to the atmosphere, the Earth is not likely to return to the state before. They will continue to increase for some time before they will decrease. So this is an example. So this is, if not reduced, it's going to increase, but if reduced, they actually slowly going down this CO2, the watts, but the Earth's temperature actually plateaued and they stay there for a short period of time. So because the implication of this is that we have to do this, if we want to curb the CO2, we want to do that early. The earlier, the less CO2 in the atmosphere, then the less time for the warming period. Okay, so this is basically the bottom line. Okay, many Earth's surface effect can be affected by global warming. So, for example, glacials, and this is an idea. So, loose snow has about 90% air compared to firm, and about 25% air to glacial ice. So, when the Antarctica, they make the ice sheet, and initially there's just snow, and then they have compactions, and 90% air is gone. They're making some kind of called firm. Firm means that they still have air. And then that after more continued compaction and also all those connections is sealed, then there will be trapped air bubbles, and then 25% of air, then they will make ice sheet. So transforming, then when it form ice sheet, it turns into something is glacial ice. So the transformation from snow to glacial ice takes about tens of thousands of years. And the effect of global warming will be a accelerated melting of glacial ice. Okay, and then the glacial ice melted, the ground is exposed, the rocks exposed, then they will have a positive feedback, which means that they will absorb, because the ice reflect more sunlight, absorb less. When you have rocks, they absorb more sunlight, and then more ice will melt it, and then the faster the warming, and then they increase the melting. So there's a positive feedback there. Once it's melted, then there's something we call that runaway greenhouse gas effect. When there's so much ice melted, then the polar ice cannot be maintained. They will be just completely melted. So in the textbook, the lowest extent of sea ice in Atlantic Ocean is in 2007, and now the new record is every year this record is being broken. And the Antarctica Peninsula is one of the most rapidly warming regions on Earth. And then you show that there are ice sheets melted, and the region covered in the rocks of ice shell, big ice shell be melted. So the ice volume in the Antarctic is it's reducing. Ice melt in different ways. Glacial melted, and there are different ways. And so there are several ways. For example, one way to melt first of all, glacial ice moves very slowly. A glacial ice basically is like a flowing ice river. Okay. And it covers about 10% of land area of the Earth. And most of them is located in the Antarctica ice sheet. and some in Greenland ice sheet, or in mountain glaciers of Alaska, so from Norway, the Alps, the South Alps in New Zealand, and so forth. So the glacial typically moves very slowly, about 1 meters per day, except the avalanche. Avalanche will be moving that much faster. These days we see that these glacial actually retreat, means that they melted, more of them melted. They more than the speed of melting is faster than the speed of supply. So the melting is faster than how much they can flow down there. The glacial moves by several processes, like basal sliding. If you're on the slope, and because of gravity, they're going to slide down. And also, they're as a base, they could have water, have rocks, a deformation, and the below certain depths, they will deform plastically. So the ice and pressure actually work like a plastic, and then they can move down, they can flow. Okay. So these are also recently there are discoveries saying that the ice sheet and lactic the basal ice, they melted and they turn into water, they lubricant this contact, and then more ice will flow. So there are many ways for this ice to move, and there are also some underground geothermal energy. They actually heat up the basal part of this ice sheet, and it will start to melt, and then lubricant, and more will start to flow. So here is example in Antarctica. So this is the ice basically melted the bottom, and the more ice melted and lubricant the baseline, and the ice sheet is formed. Iceberg, or big iceberg will form. And also when the glacial, also the agents of erosion, just alpine and valleys, they can convert V-shaped valleys formed by river erosion to U-shaped valleys. This is an example of the famous Yellowstone. So the Yellowstone National Park in Wyoming, this Yellowstone River formed this kind of V-shaped valleys, whereas this is the U-shaped valleys in California, Sierra Nevada. And you see this become U-shaped, and then inside they're also forming some kind of glacial lakes. Also, it's actually eroded by glacial. So during the global warming, permafrost is thawing. Permafrost is basically the permanent frozen ground. And sometimes we call that permafrost. This is a very widespread natural phenomena in high northern latitude, above 90 degrees, under 20% of the land area in the world. And there's two kinds of permafrost. One is called discontinuous, one is continuous. And defined based on the area extent of frozen ground. If continuous permafrost areas, Greenland, North Asia, the only ice-free ground is beneath deep lakes or rivers. The river can keep the ground from freezing. And if we go into south, further south, and you see that this discontinuous permafrost occurs in high latitude by scattered islands or a thawed ground in a predominant frozen area. And the permafrost varies from north to south in thickness as well as in continuity. In the north, it's more continuous and thin, whereas in the south, it's more discontinuous and north is thick, and up to about 400 meters in the south, sometimes less than 0.3 meters. So when they are melted, like this in Canada, they are forming this kind of, we call that the tundras, and little lakes, and also ice and puddles, ice. And this is because when they melted, the underground has ice and also methane were released, and they form this kind, we call it tundras. Okay, small lakes, and this is one reason why Canada has the most lakes in the world. So the figure you see here is what's called permafrost damage. So originally, the house was building a platform, but however, it's building on a flat surface. However, the thawing permafrost, the ice melted, the methane, the gas come out, then the volume, the losses to some space, then it's going to subside. And that's basically a result of poor construction practice in Alaska. Here is a picture showing what's called differential subsidence of a gravel road near Alaska. And then it used to be they built a road, and then they didn't realize that didn't anticipate the melting, thawing of the permafrost as a result of global warming. And then you see that different places have different substance, and then the road very quickly becomes a roller coaster. Again, it's not usable anymore. So you have to use a different kind of strategy in order to build a road in Alaska. Another interesting thing is due to global warming is something called loess. Loess is something called, it's a blowing deposits, and then normally can be divided into two categories. One is the sand deposits, the other one is loess. So sand deposit, basically that's a sand, desert, and their finer grains are loess, like a dust. And in contrast to sand, which rarely moves more than 1 meter of the ground, windblown silt or dust can be carried in huge dust clouds, 1,000 meters in altitude. And a typical dust storm, 500 to 600 kilometers in diameter, carry more than 100 million tons of silt and dust. And that's sufficient to pile a 30-meter high and 3 kilometers in diameter. So these are, this is example of the loess in United States. And these are, most of them are in the center part of the United States, Mississippi, Kentucky, Tennessee, Illinois, Missouri. So actually you see that it's more than 20 meters loess happen in Nebraska, Kansas area, very thick. And these are due to the large glacial maximum, and then when there's the glacial deposits, and then lots of them are very fine grained, and then when they are their winds, strong winds there, then it will be blowed everywhere, then they form this kind of loess. Okay, so these are actually related to the glacial and the retreat of glacials, and then those material will be blown around. So melting glacial ice, sea ice, I mentioned before, mountain glacial are retreating, affect the resources, and also can cause sea level rise. So this is an example showing the figure of Greenland glacial. The difference is 90-40. So you see the glacial all the way up to this glacial lake here, okay, here, all the way to here. And here is still, at the time, you still see the waterfall, the glacial, the tons of the glacial is right over here. And in about 66 years later, and you see it's only on this platform, and most of the others already melted away. So we know that the mountain glacial are retreating, and melting ice of a Greenland ice sheet has accelerated since about 1998. So this is sea ice, and in Antarctica, 2007, it's actually much smaller. In 1953, it's a much bigger area in Antarctica, and now every year it's going to be smaller and smaller. And in the summer, Northern Hemisphere summer, some people actually predict that by the end of the century, the Arctic ice is gone if we don't do anything. It's business as usual, then this will be gone. But this is highly debatable because some other people has different kind of models and modeling saying that this is not necessarily true. But it's shrinking, that's for sure. As the Earth warms, more melting and there's more precipitation. And in Antarctica, things are a little complicated because as more melting, there's more as Earth's getting warmer, there's more melting of Antarctica ice. At the same time, Antarctica has more precipitations and there's more moisture, then so there's always competitive force that to either increase or decrease the volume of ice sheet in Antarctica. But as it continues to warm, then eventually the melting will be more faster than the precipitation. Thawing permafrost in Siberia and Canada is releasing carbon dioxide and methane that are trapped in permafrost that further accelerate the global warming. I just came across a recent weather recent video from the weather.com, and then they try to compare the big lakes, the volume coverage of the big lakes. Normally in February, March, a large part of the big lakes are frozen, and then they basically measured the area, how much area they covered, then compare from 2014, March 2014, compared to today, not today, this March 4th, 4 days ago. So you can take a look at how much difference they are. So you get a picture that even those big lakes, they used to large portion of the lake has been frozen in winter, and these days, not the coverage reduced by 10%. It's okay. All right. So next question is the change in climate patterns. So global warming leads to significant change in rainfall and soil moisture, it causes drought and flood, and agricultural activities like crop growth cycles and world food supplies can be affected really by climate factors, desertification, natural hazard like hurricane and other storms. When we talk about hurricane and other storms, we're going to spend more time on this. So first is desertification. Desertification is basically the arid island or arid lands, the semi-arid region of the Earth, and also known as the dry lands, occupy approximately 35% of Earth's land section. Lives there, and dry lands are environmentally important to people. There are 5 different kinds of desert. One is subtropical high zone like Sahara and Kalahari, Namibia, and part of Australia. They're actually sitting right in the high pressure zone. Therefore, they have desert. And then there's a continental desert, and in continental interior, far from moisture, continental desert. And then there's rain shadow desert on the sheltered side of mountain barriers that trap moisture airflow from oceans. So it's called rain shadow, or sometimes we call it orographic effect. And there's also coastal deserts, continental margins, where cold uplying marine water cools maritime air flowing onshore, and also polar desert in the polar region because it's very cold. Therefore, the air is very dry, creating very low precipitation desert. Now, when we talk about the desertification due to global warming, we can't control these subtropical regions. Maybe the subtropical region will be wider, and these desert is not basically not affected, but continental ones will be affected, and also the rain shadow ones could be affected. So the sand dunes can be blown, and related deposits are found along the coast of the Atlantic and Pacific Ocean and the Great Lakes. And desertification is basically conversion one type of land, such as grassland, to land that resemble when we have a more dry environment, less trees, less water, then you have dust storms. This is in Kansas in 1935. And also this is dust storms. Okay. And so these are when there's dust after the dust storm, and people have to clean up the sand, which is piled up by blowing from some areas. And because the desert are expanding, less trees, the desert definitely expanding. Sea level rise. Now, sea level rise is also a very big topic, and it's a reason of global warming. This is potentially very serious problem to global warming. the global ocean is about 4 kilometers, and it has increased. The depths of that it has increased since 1961. The world ocean absorbs about 4/5 of the heat that's been added to Earth's climate, the water to expand. So the sea level rise there are 2 issues here, two reasons here. Number one is the melting of glacial ice, and it has been studied that in the last 50, 60 years, that effect is actually not a lot. Rather, there's a second effect is thermal expansions. So the water, when they heat up, the density will decrease. So with the same mass, then the volume will increase, right? So because that, the sea level 80 centimeters wide range of rise in for the next century that's been predicted. In 1960s to 2003 is estimated to be 0.4 millimeter per year. That's calculated. It's about 30 to 40 centimeters increase of the ocean sea level, then due to thermal expansion, and most of them are not due to the melting of ice. If the first of all, the Arctic ice I mentioned before, Arctic ice entry, but what melting of Arctic ice is not going to change the sea level. Okay, if you think about physics, that's because this Arctic ice already floating on the ocean, so melting of that does not change sea level. Whereas the continental ice, like out of sea level rise, for example, Greenland, if all Greenland ice melted, it's been estimated like sea level rise, not just purely due to the ice sheet input, that will increase about 30, 40 meters. Whereas Antarctica melted, that will increase about 60, 70 meters alone to make it even higher. So the estimate for the next century, 40 to 0.4 to 2 meters of sea level rise will be can happen. That could be a huge problem. The problem are, one thing is some island can disappear. So for example, this is example of this small island in the tropical Pacific Ocean. That's called Tuvalu atolls. Right now they're like this. They don't have trees and like a very long line. In the center, basically they're fringing corals there, and inside they're relatively shallow. Outside is quite steep. A rising sea level since last glacial maximum about 20,000 years ago, that actually overtopped the degraded carbonic platform. So inside they're actually a shallow water place, and then outside is deep water. You can see the color differences. They're deep, dark blue. This green is quite shallow, and the highest place on the island is only 4.5 meters above sea level. 4.5 meters above sea level, and people first another atoll of Tuvalu about 2,000 years ago, and one stable inlet formed, 47% of sea level rise is now threatening the food, and people here, a lot of time they have just, I guess the only transportation is to swim, in the water, and there's not a high ground, and there are 12,000 people living off of the foodie, and once the sea level rise, they probably will be the first to be displaced by sea level rise. The increase in coastal erosion, and the coastal erosion including things like the land shift to existing estuaries. The estuaries will expand towards the land, and then that will impact the existing development along the coastal zones. Another interesting thing about global warming is the El Nino. El Nino is start from the latitudinal distribution of the heat. It's longitudinal, and because Earth's wind system in the equator blows the easterly wind, so the warm water can be blown to the west part of the Pacific Ocean, for example, and then the heat will be actually the surface water are hotter, so they will be blown to the west part of the Pacific Ocean, where they cause more evaporation and then have raining. So this is a normal condition. This is what happened. This east wind is slowed down, and this center, the warm water pool, and going to center part of the Pacific Ocean, then we have something called El Nino. El Nino is longitudinal distribution of this warm water pool. That's something to do with the trade winds, and the reduce of trade winds cause the warm water to move eastward a little bit, and then El Nino was established. When El Nino established, then drought, whereas in the South America used to have a dry condition, now all of a sudden you have rains, then become to be wet, flooding happened. So it's the longitudinal distribution of the heat. So people predict that during global warming, then there will be more frequent change between El Nino. La Nina will be opposite. If the trade wind becomes stronger, then these hot warm water coming even further to the west, then comes something called La Nina. Then places like Asia will have more raining, and we have La Nina. So biosphere can also be affected by global warming that can cause number change in biosphere, both people and overall ecosystem. And then there's a risk of extinction due to land use change and habitat shift, like from estuaries to ocean environment to estuaries, and due to the sea level rise, organisms, for example, mosquitoes carrying disease, including malaria and dengue fever in Africa, South America, and Central America. They are migrating to higher elevations, and butterflies species moving northward in Europe, some bird species moving northward in the United Kingdom. Then there's a subalpine forest in the Cascade Mountains, Washington, migrating to high meadows, and so forth. So polar bears, walrus, seabirds, and they have huge stress because the Arctic ice is melting. So then there's also warning and increasing Australia then can have effect on the bleaching of coral reefs. So and both land and ocean component can be affected. And the global warming can cause a number of change in biosphere. So one very important thing of change for the ocean is something we call ocean acidification. So as by ocean, then the dissolved CO2 with ocean forming carbonic acid, and carbonic acid can release a hydrogen ion there, and then cause the global acidification. And the global acidification causes a huge stress on the corals and the marine organisms that use carbonate as their shells, if the ocean acidification make them to spend a lot of energy to make those shells, and without shells, they are not protected. So they will be easy to get extinct or die. So during the last 25 years, also plants and animals shift their range by about 6 kilometers per decade towards the polar areas. So basically they're migrating. Spring arrival earlier, migrating birds are arriving earlier, about 2.3 days per decade. In Costa Rica, over 60 species of frog may have gone extinct. So something we can do is to assess migration of some species. And some of them probably unable to migrate with climate change. Or when they migrate, they could create invasive species, and so they can cause some problems. Okay, so next question, global warming. So first, we have to identify historical change that have occurred. We have to learn the geology, the Earth's past. Then we evaluate the parameters of climate, frequency of storms, sea level rise, biological effect, economic effect, social, political effect. And then we can sort of predict what change will occur. And one of the biggest important thing is try to reduce greenhouse gas. And this is a political commitment, and reconcile the conflict between environment need for reduction of greenhouse gas and economic demands for more fossil fuels. So one of the problem here is that we know that fossil fuels is relatively cheap, and they're the engines of the economy. And also we know that there's effect of emission of greenhouse gas due to fossil fuel burning. So these two are, we have to, these are become to be the major problem, either political problem. I have to say global climate change is a political problem rather than, and also social and economic problem rather than a scientific problem, because we know the science, okay, quite well. And so because there are different political agreement, like this Kyoto protocols. So in 1997, United Nations Framework Convention on Climate Change in Kyoto, Japan, the objective of the convention was super, especially carbon dioxide. The United States originally agreed to reduction, but in 2001, it refused to honor the agreement, much to the disappointment of other nations, especially European allies. As a result, the leadership in controlling global warming has shifted from the United States to European Union. But one of the reasons is that some other countries are one of the biggest CO2 emitters. So they have to, then some of them, if some of them are not committed, then other country might find a bigger commitment. 2005 February, the Kyoto Protocol was signed by 166 nations, become a formal international treaty in February 2005. The United States, as of 2010, has taken more active steps to deal with climate change through energy planning and reduce carbon emission. And we mentioned before, we face a dilemma, is that fossil fuel on one hand are vital to our society, and are necessary for continued economy. Scientific evidence suggests that burning fossil fuel is contributing significantly to global warming. And here is something called peaks of CO2 emission 1,500 years, 100 years. So this eventually CO2, if we take actions, CO2 emission will decrease. And then, as you can see, sea level will continue to rise, even though the CO2 is actually emission decreased, though it's decreased. So they're as lag times. So even though we reduce CO2 emission, then the temperature is not gonna drop almost instantaneously. It continue to rise until we reach a plateau here. And sea level will continue to rise is because the melting of glacial and also thermal expansion as the sea level actually take a much longer time to stabilize. And also the post-glacial rebound and so forth. And many factors can contribute to sea level stabilization. So even if carbon emission were reduced to zero, warming will continue this century. There's a 0.5 to 1 degree in the system. So this is even though the CO2 and we still have continued to increase temperature and also continue to increase the sea level. In 2015, there's a Paris Agreement. Basically, that's a legally binding international treaty on climate change. It was adopted by 168 parties at COP21 in Paris on December 12, 2015. And it entered into the force on November 4th, 2016. The goal is to limit global warming to well below 2 degrees, okay, preferably 1.5 degrees Celsius compared to pre-term temperature goal. Countries aim to reach global peaking greenhouse gas emission as possible and to achieve climate neutral world by mid-centuries. In the beginning, when Obama was president, he actually for this Paris Agreement. Then when Trump would become president, then he basically walk away from this treaty. Okay, strategies for reducing global warming. There are several strategies we can use. So one way is to reduce emission through improved engineering of fossil fuel burning power plants, develop and use coal burning power plants. This table shows that fossil fuel, there are 3 kinds of fossil fuels. One is coal, oil, and natural gas. This is estimated like these days, 36% of the carbon is from coal, 43% from oil, but 21% from natural gas. However, coal is actually the dirtiest one. They release much more carbon per unit energy than oil and gas. And also coal, inside the coal, there are metals pollutions cause release 23% less of energy than coal, and 28% natural gas, 20% less than oil gas. So from this, you can see that natural gas is cleaner than the oil or coal. And so this is something people think that they prefer using these days, using natural gas. But although natural gas has other problems like fracking and can cause other problems. Now, coal is dirty, so we have to scrubber or basically sequester the carbon and place it in a safe storage. And also these days, people propose to use fossil fuels that release less carbon, and we can conserve energy to reduce dependence on fossil fuel. And also we can store some carbon in plants, soil, and ocean, and receive some studies. An option to sequester carbon in geological rock environment has less attention. And there's straightforward is to capture carbon dioxide from power plants and industry and inject that carbon into the subsurface geological environment. To environment receive some, so this is reducing, improve engineering using fossil fuel, releasing CO2, conservation energy, store in forest, CO2, use alternative energy. So now there are 2 places people these days. One is the oil and gas field, using the CO2 to pump them, then introduce more pressure. So there will be more recovery of oil and gas. That's one use. The other one is pumping the saltwater aquifer. Eventually, CO2 can react with the salt water, then turn into some kind of carbonate, and then eventually we sequester them. And in the United States, last class, we'll talk about mineral resources. We said we have lots of saltwater aquifer, and we can do that. Okay, the last question is about coupling of global change and processes. Example, which is the ozone. Ozone coupling the greenhouse gas and the ozone depleting problem from CFCs. CFC is the chlorofluorocarbons, and most of them are coming from like furans from our refrigerant. These days, it's not allowed. Refrigerant liquid cannot be CFCs. It's been replaced by other non-CFCs. Use this. So the coupling of gas, and even though carbon dioxide is a predominant factor changing climate, but these are all greenhouse gas. Now, but ozone has a special purpose, especially when it's in the troposphere. It's not good. It's actually a toxic gas. But if they're in the stratosphere, they actually help protect the organism from UV, shield from UV light. But these chlorofluorocarbons, they're in troposphere at low temperature, they're actually quite stable. And whereas in the stratosphere, they are decomposed. They will become to radicals, chlorine, and these radicals combine with oxygen, ozone, and forming chlorine oxide radicals, and then they combine, forming oxygen, and then return back to chlorine radicals. And then they will have catastrophic effect. These will reduce the ozone by a lot and forming ozone holes. Then even though ozone is in the troposphere is actually pollution, air pollution, where in the stratosphere is actually beneficial for humans. Okay. So so this is these days, of course, we banned using CFCs as refrigerant, and this ozone depletion reactions like Antarctica before, and other places had ozone, and above Antarctica, South Pole, now South Pole, you have a ozone hole, and that's it's the CFCs. It's a greenhouse gas, and also is affecting the ozone depletions. So if we get rid of CFC, we reduce the greenhouse gas, and we also protect the ozone, which is good. Next is fossil fuels contain sulfur dioxide, and then when they are forming aerosols and then combined with rainwater, then they cause the acid rains. Using fossil fuels, eruptions can cause cooling, and fossil fuels, if we generate the soot and then they can reflect the sunlight, can cause cooling. And again, we see the principle of environmental unity in action, which means that many aspects of one problem, in this case, the global warming, are related to many problems, such as ozone depletion, CFCs, greenhouse gas, and the acid rain, and so forth. Climate change is defined as large-scale change in global climate system that take place over a few decades or less. Such change is anticipated to persist for at least a few decades and will cause substantial disruption to both human and natural systems. That's called climate change, abrupt change. The rapid change in sea level as a result of change in glacial and ice sheets, hydrological cycles, abrupt change in pattern of circulation water ocean that is characterized by northward flow of warm solid water in the upper layer of the ocean, and rapid release of methane. These are the 4 questions that are particularly concerned, and that's been in the abrupt climate change. So as we talked before, if you look at Earth cycles, Earth has its own ecosystem that can alter the concentration of CO2 in the atmosphere or greenhouse gas in the atmosphere. So we have glacial interglacial cycles. Those are natural cycles. However, because of anthropogenic CO2 greenhouse gas emission, then we actually these days have an abrupt climate in the atmosphere too fast. So that can potentially have these problems, these issues. So in this chapter, there are many contents. This time you can answer 2 questions. One is that in written form, once rapid economic development, developed countries have expensive environment, should people put environment issue first? Why not? Second question is, what are major ways to reduce emission CO2? Okay, again, I'm a little late, so I'm probably going to postpone the midterm exam by 1 week. Okay, and also it's time to review.